All right, so the past few topics have kind of started with tectonics, talked about how rocks are created, uplifted, brought to the surface, and eroded. And so the next topic we got into in depth was weathering and erosion specifically. And it started with this topic of the critical zone, which is really where the solid Earth meets the ocean atmosphere system. And so in this region, rocks encounter things that they don't encounter in the subsurface. You know, essentially, the keys there are water, gases, acids, and low pressures. And so rocks are under a tremendous amount of pressure and in a relatively homogeneous environment in the Earth's subsurface. But at the surface, they experience all of these really variable conditions that lead inevitably to the breakdown of those rocks and minerals over time. And so we separated weathering and erosion into two separate camps. Weathering is really the suite of processes that break rocks down, and then erosion is really specifically the transport of those breakdown products, essentially down slope, right? Gravity takes everything down, and in a practical sense, that means eventually to the ocean in most instances. And so that really creates this idea of tectonics uplifting mountains or just bringing terrain up to higher elevations where it experiences physical and chemical erosion, and then water and wind transports that material down until it's deposited in the ocean, right? And there's this variable amount of space in between the site of erosion and the inevitable site of deposition, where the terrestrial biosphere exists essentially, and throughout this entire region, soils develop, right? And so we really talked about two specific weathering types, physical and chemical. Excuse me. Physical weathering processes just break pieces down into smaller pieces. Okay, and so you have a big cube here, and it breaks down into some smaller cubes here. That's a physical breakdown. You're just making smaller pieces, and that's really important because a smaller piece has a higher surface area to volume ratio. And it's on the surfaces where chemical reactions take place and chemical weathering progresses as a result, right? And so we use this example of a hard candy like a gobstopper. The fastest way to dissolve it or to eat it is to smash it into a bunch of little pieces. And so there are a variety of physical processes that lead to the breakdown of rocks or the breaking of them into smaller rocks, essentially. Frost wedging is a big one. That's where water gets into a crack and then it freezes, and when water freezes, it expands, and so that causes the rocks to break. There are also a variety of other things that can cause kind of wedging in rocks. Roots are really good at this, so vascular land plants do a really good job at enhancing physical weathering. And salt can actually do this as well. These are fence posts in a dry lake bed, and the crystallization of the salt is causing expansion within that wood. Okay, and this idea of thermal shock gets back to the fact that in the Earth's subsurface, rocks are under a tremendous amount of confining pressure, and that's what they're really used to. And so when they get to the surface and the pressure is reduced so much, they have a tendency to just kind of crumble on the edges. One word for it is exfoliation fractures, something like that. But it creates these fractures that are parallel to the surface of the rock. The rock tends to just kind of flake off. But all those in general produce smaller pieces, which have a tendency over time to go from being angular to more rounded. And so the more rounded a piece of rock or a clast is, in general, the longer it's been kind of weathering or the further it's been transported. Oftentimes it relates to that. But going through these slides, so another way to think about this is just this is like some type of crystal structure here. It looks like sodium chloride, to be honest, but physical processes break this larger crystal into smaller crystals, right? That's physical weathering. Chemical weathering differs in that, or from that, in that it breaks a mineral down into its individual chemical constituents. Okay, and so if this were sodium chloride, the mineral halite, which it kind of looks like, it's a solid mineral, salt, as sodium chloride, but if you dissolve it in water, it turns into chloride ions and sodium ions, single charged ions in solution. It's dissolved, right? And so you can think about the process of weathering and transport in general. Rocks are uplifted. There needs to be some topographic relief in order to drive weathering, essentially. Doesn't, I guess, need to be, but it certainly helps. But the process starts with breaking down rocks. Acids and oxygen and other reactive species in the environment will cause a rock to dissolve. Parts of the rock will dissolve more easily than others. Specific minerals in particular will dissolve more easily than others. And so over time, you get kind of a sorting of the easy to dissolve minerals go into solution, they get dissolved, and the remaining kind of residual minerals that are really resistant get transported. Over time, they get rounded and they turn into sand or silt or clay, but most clay comes from secondary transformation. It's a weathering product, actually. And so over time, you take the initial minerals and you dissolve parts of them away, and what remains is these secondary clays or these really resistant minerals. And that's really captured, let's see, on this slide here, and this is where I'm going to cut off this video. But you start with these igneous minerals, things like pyrite or olivine. Well, not necessarily pyrite, but olivine and pyroxenes, feldspars, things like that. Those are unstable on long time periods, and so they dissolve. These kind of salt minerals are very rapid dissolving, but these silicate minerals dissolve fairly rapidly, and they turn into these more stable minerals like clays, oxides, and similar weathering products. And so over time, you start out with a rock, right? If we think about this back in the context of this slide here, you start out with rocks in a high relief, high topography, right? Like in the mountains. They break down physically over time. They chemically break down. Whatever is soluble dissolves into water and is transported to the ocean. Whatever is left over just gets transported by physical processes, either as a particle in a stream or it's blown by the wind. And all the while, there are processes working here in the terrestrial environment along this stream, right? There's soil development and a whole biosphere in here, a whole lot of plants and things. So the next topic that this leads naturally into is soil development, and so that'll be the next video there. But this process takes maybe 10,000 years to transport sediment. It might take millions of years to actually break down a mountain range. The Appalachians, right, were formed hundreds of millions of years ago. And there's still some topographic relief there, right? There's still weathering and eroding. But over 1 billion years or so, without tectonics, you would run out of mountains to weather, right? And so it's really tied back into that. And without this weathering, the flux of weathering products, you would run out of some bioessential elements, some nutrient elements in the biosphere. And so it's critical for that as well.